Okay, everyone. So I think let's get started. I think a couple more people might trickle in, but let me just, it's my pleasure to introduce Bryan Roberts to give the BHI Colloquium today. Bryan is professor of philosophy, logic, and scientific method at the LSE, the London School of Economics. For those of you who don't know, the LSE's Philosophy, Logic, and Scientific Method department is a storied department founded by Karl Popper and has always done fabulous work in philosophy of science. Bryan got his PhD in history and philosophy of science from the University of Pittsburgh, and he has been faculty at the LSE. Between 2019 and 2020, he was fellow of Trinity College, Cambridge. And from 2019 to 2022, he taught in the Part 3 program of the Department of Applied Mathematics and Theoretical Physics at Cambridge. Bryan works on a wide range of topics in the philosophy of physics, including but not limited to the philosophy of space-time and philosophy of quantum mechanics and many other topics. And today, Bryan is going to tell us why black holes are hot. So please welcome Bryan Roberts.
Okay. Wow, what a pleasure to be here. Thank you for inviting me. Thank you to the organizers, Siddharth and Nicole, and to Peter Gallison, the director, for having me. It's my first time to the Black Hole Initiative, but I've been a fan from afar of many of you and of what's happening here. And also, I guess, hello to the YouTube watchers. This is a coveted place to be, a very popular YouTube channel. Those watching for the first time, remember to like, comment, subscribe. As a fellow YouTuber, I know this is a difficult thing to maintain, but actually it's an enormous service to the community. I follow this channel regularly, and it's really nice to stay connected to what's happening, especially in North American physics and philosophy. So this is a talk that came out of me thinking about what was hot. That's one aims to do, isn't it, in science and philosophy? And I ended up with a view about black holes. There's a paper here that is more about how I think about what's hot on the archive, with the black hole thing sort of in progress right now. These slides you can follow along online. So this is like an online presentation. And I'm running a grant now, which is close to the documentary that Peter did some years ago in Spirit, called the Edge of the Universe Project. It's studying boundary conditions in large-scale structure, space-time, and black hole thermodynamics issues. And there's a visitor program, so potential for collaboration. Just wanted to flag that. So let me launch off with a Just So story. This is something that's going to be familiar to those of you who are working in black hole thermodynamics, and to those of you who want to get into it, soon will be familiar. The Just So story says the black hole thermodynamics was a mere analogy when it was first thought of. And then Hawking radiation came along, and suddenly that was really thermal. The kind of key papers that one tells when describing this story are these ones. Bekenstein, while writing his PhD thesis under Wheeler, wrote down the second law of black hole thermodynamics. But we usually say about this that this is kind of like a reckless analogy to ordinary thermodynamics. He was motivated by the area theorems, the idea that something is increasing here. In this case, the area of a black hole over time. And hey, so does the second law of thermodynamics. And so he formulated the generalized second law for the first time. Bardeen, Carter, and Hawking complained heavily about this in the sense that they really emphasized this is just an analogy. But they went on to give 4 laws of black hole thermodynamics, which again, they insisted at the end, these really are just analogies. One mustn't take them too seriously. And then, really shocking the community, 1974, Hawking shows that black hole particle creation is possible. Now doing a statistical mechanical analysis, he writes down an equilibrium state associated with a temperature that's proportional to the surface gravity of the black hole, the so-called Hawking temperature. And this is when things get really thermal. Okay, so this is the just so story. I know lots of you have heard this before. And I just to emphasize at this stage as well, notice the transition from thermodynamics qua thermodynamics. You know, sometimes we mash thermo and stat-mech together, but I'm separating them a little bit in this talk. Think about thermodynamics as the thing that was developed by Carnot and Clausius and Kelvin and Planck, deals with heat engines, variables like volume and pressure, whereas stat-mech is the statistical analysis of a dynamical system with some set of observables that allow you to coarse grain it. And so we've really made a transition from reckless analogy regarding thermodynamics to, well, really thermal in the stat-mech sense. And I'm going to challenge this just so story today. I'll just flag it for the moment that there are some tensions in it. Firstly, thermodynamics, the science of Carnot, Clausius, Kelvin, and Planck, was invented before statistical mechanics was, really well before. And before we were even confident that things like water and gas were molecular in nature, that they were made of sort of atomic parts. And yet it worked fine and had its laws. Secondly, heat is central in thermodynamics. We're talking about whether something is really thermal, really hot. But it's kind of an afterthought in stat-mech. Central tools of analyses aren't really about heat, but perhaps more things like temperature. But the main thing I want to say about this just so story is that there's a better story available. It begins with a clear perspective on what thermodynamics is. So I will argue for a position on thermodynamics that would help clarify what kind of theory we're talking about when we use it. It says something like thermodynamics is the science of heat as unobservable energy. Now, the first time I gave this talk recently in Nottingham, I said hidden energy. And I had the bad experience that they didn't know me that well. And they were like, okay, a philosopher talking about hidden energy. This is going to be a crazy person talk. So I switched to unobservable, and it is in a sense more to the physical notion of unobservable that one finds in quantum mechanics. It's not really so much about an observer, though. It doesn't have to be. It's like in quantum mechanics. It represents those degrees of freedom which are in some way accessible, associated with some measurement devices. But you don't have to introduce an observing agent in order to understand quantum mechanics. Just think about the structure of observables. So I mean it in that sense, and we'll talk about it more. The second thing is that on this view, even without stat-mech, there is a sense in which black holes are really hot. And I would like to tell you about that. Let me now switch to a personal moment in the talk. There's a lot of reasons why I need therapy, but I wanted to tell you about one of them. And this talk is in a way a bit of progress towards that therapy. When we first learn general relativity, we start to say things like the world is a Lorentzian manifold with some fields on it, tensor fields, spinor fields. When we introduce quantum mechanics, we say things like the world is a Hilbert space, maybe with an algebra of observables. And if you're really, enlightened, you might say something like, well, actually, all I needed was the observables and maybe a preferred state. Very mathematically precise and clear. When we do gauge theory, we say things like the world is a vector bundle with a connection that allows us to state the Yang-Mills equations. But when we talk about thermodynamics, we say things like, let there be a semi-permeable membrane in contact with a heat bath. And for those of you who, like me, budding young mathematicians, encounter this kind of language, you'd be like, what is this, and this, until you're pulling your hair out. And this led mathematicians, not just me, but also the great mathematical physicist Vladimir Arnold, to say, every mathematician knows it is impossible to understand an elementary course in thermodynamics. So when I was a PhD student and I first encountered this quote, it was a quote somebody was giving in a paper. I think it was Yosu Fink. I was like, great, what a relief. I'm not the only one. I can relax. I've done my job to understand those other theories, but this one is like, why try, But then later I got my hands on the paper. This is a good lesson to the historian. So I'm also a historian of physics. You should always read those original sources. And what Arnold says wasn't quoted in Ufink, in the very second sentence right after this one is, the reason is that thermodynamics is based, as Gibbs has explicitly proclaimed, on a rather complicated mathematical theory on contact geometry. So Arnold wasn't actually saying it's impossible to understand thermodynamics, just not in the first course, which is too elementary. You've got to work a little harder, get to your advanced courses, and then you can understand it. So I'm going to tell you a little bit about that. I'll briefly flag that this, for some of you, might have heard of highly mathematized approaches to thermodynamics. Usually when one speaks that way, one thinks of Lieb and Ingvason and the so-called accessibility relation approach motivated by Theodori and others. I'm not going to talk about that. That is in a way a very austere program, very virtuous. It does connect to what I'm talking about, but this is going to be a talk that's much closer to physics and to language that's familiar, so I find it better. So the new proposal on the road to recovering from the trauma we went through learning about thermodynamics for the first time is that the world it can be described as a mechanical system with some observables, and where some of the energy is unobservable with respect to that set of observables. And there is a sense in which thermodynamics falls out of this idea, and I will show you how that happens. So this is going back to an old example, really due to Gibbs. If I'm trying to understand a little chunk of energy associated with a weight on a block, it's very simple. I need to understand the pressure on that block, on the surface or with respect to the whole volume. But when I switch the wood for a gas, something strange happens. Now, this is Gibbs writing in the late 19th century at Yale. It heats up. And that would seemingly violate a certain conservation law. It would seemingly allow us to extract energy out of the system and spin a flywheel if this PDV term was the only bit of energy that mattered. So it's as if there's some hidden energy, unobservable energy, and we'd better add it back in whatever it is. We're writing at a stage where we don't know what gases are made of. We certainly haven't adopted the atomic hypothesis or the molecular gas hypothesis. It could have been a continuum theory all the way down. So we'll just write a term, psi, that's a one form, mathematically, that represents heat. It represents that extra energy. Sorry, I'll call it heat, but it just represents that extra hidden energy, whatever it is. Now, in your thermodynamics texts, you often see this slash dq notation. I really don't like that notation. It's sort of, I always miss the slash and think it's an exact one form. So the mathematician in me just can't abide this. So I'm afraid I've switched the familiar language to psi. Also, it looks like a little hot, sort of vapor coming up, doesn't it? So it's a nice switch. I think you'll stick with me and understand this is the heat one form for the rest of the talk. Now, secretly, you and I know that there's a phase space underneath this gas, and it consists of a roiling mass of molecules hidden from sight. But if I were to try to describe the energy of those, countless molecules, I could put my best grad student on it, but it's going to take me a long time. I've got to write down, so this is the sort of expression of work, mechanical work for the system. I've got to write down the pi dqi's for all of the 10 to the 23 molecules in the gas. Impractical. But sometimes, yes, go on.
Sorry. Are you assuming that the gas is made of molecules?
I am looking at an ordinary molecular gas right now, and I'm going to soon move beyond that. But yeah, I'm assuming there are some degrees, where I will come to is there are some degrees of freedom. So you should view the Q's as canonical configuration variables and the P's as the canonically conjugate variables to each. Those could represent the positions in three-dimensional space of a molecule, like when we think of an ordinary gas. But the same analysis works in a quite general context, even for an infinite list, meaning I've got something like a field theory, where I have really quite a lot of Q and P variables. And generalized configuration means it doesn't have to be position in space. It could be any degree of freedom associated with some measurement. Right, so I've got this big long list, but also I might have in my laboratory some particular measuring devices that allow me to identify some of those degrees of freedom. these are my I think that here on the site of the Event Horizon Telescope, I am pained to have drawn these kinds of measurement devices, sort of like philosopher's first approximation. I've got a ruler and I've got a pressure gauge. And while that does help me say something different about certain of these variables, and that is that I can measure them. So with these two devices, it might be that, again, just thinking in terms of canonical configuration and canonical momentum, there might be a variable that I'll just write it by convention as big V that's measured by the ruler. The ruler can help me measure things like volume. And big P that I can be helped to measure using my pressure gauge. That's the pressure. And then I've got the remaining degrees of freedom. If these are my only measurement devices, I just can't measure them. They're outside the scope of the analysis. Yeah, Jacob. I haven't said anything about units or whatever units I want, right? This is a generalized configuration variable. So don't think yet in terms, I haven't even defined work yet. I'm literally just doing mechanics at this stage, but I will define work in a second. And then there's a space on which your question can be answered.
I guess conceptually.
Okay, sorry. Yes, we will get to that. Yeah. Sorry, I see what you're saying. This is expressing mechanical work, and there is a sense in which mechanical work allows me to capture. Sorry, now I understand your question. I didn't understand before. It allows one to capture the conservation of energy requirement. That as one traverses a closed loop, the total sum of this mechanical work is zero. That winds up being equivalent when you make this a dynamical system and consider it in Hamiltonian formulation, that is equivalent to the energy being conserved. So I'm looking at this as a little chunk of work, you call it units of work, but it stands in for a measurable aspect of energy which is conserved and allows me to express the conservation law.
Okay,
Fair enough. Again, it's a stand-in for an aspect of energy, if you like. So let's think of this in terms of mechanical work, if you like, and switch what I said about
I
energy.
think of the piece as general.
Yes, yeah, sure. Yeah, I mean they are generalized configuration variables and momentum variables. But you see where I'm going with this. This is an expression of a mechanical system. I've identified some of these variables as measurable with respect to my measurement apparatuses, and some are not. If I had a different list of measurement apparatuses, I might have more variables here. So someone might have a lab that allows them to measure electric charge or chemical potential. And these sorts of things would add to the list of measurable contributions to, well, mechanical work. But for now, let me just take the simple case. It can be generalized easily and collapse together and use this term omega. Sorry for the Greek language speakers. It's really should be a word that starts with O, but it kind of looks like a W. So I'm thinking of it as a work term. But work in the sense of being accessible to my measurement devices. And then I've got this list of non-measurable stuff. I've just changed the name of the variable here to du. And then I take all of this non-measurable stuff and collapse it down into what I defined the non-measurable contributions to be. That is psi, the heat one form. And if you rearrange this equation, you are looking at the first law of thermodynamics. So sometimes we say about the first law that it expresses something like conservation of energy. I would rather look at it as expressing a decomposition of energy into work components that are accessible to my measurement devices and heat components which are not accessible to my measurement devices. They are hidden, they are unobservable with respect to my set of observables. So the definition of heat changes with your observables. You change your laboratory and what can be measured, you change what heat means, you change what work means. That makes sense on this picture. And this is what led me to say this aspect of my thesis, that heat is unobservable energy. There are various ways that this can happen. Some people have argued that heat is the energy of microscopic molecules like Kelvin. That works in its context, but it's also that general. It doesn't obviously apply to all kinds of heat. For example, we will see soon black holes are an example of this. Heat can be viewed as energy of unknown information. Heat can be viewed as the energy of uncontrolled variables. Let a thousand flowers bloom. I'm into all of these things. But to me, they are all just examples of how heat is unobservable energy. So I take this view to be a nice generalization that allows one to capture and look at, there's a literature amongst historians and philosophers of thermodynamics investigating what exactly heat means in thermodynamics. I see this as a sort of unifying project for that literature, which allows us to add some statements we weren't easily able to add before, like heat could be that energy that is unobservable in a black hole exterior for a distant observer. And I'll talk about that in more detail in just a moment. Yeah, Sitat.
So there's no constraint.
No, absolutely not. It's rather associated with observables. Yeah, to me that's essential because, well, I mean, a black hole is rather macroscopic, as a structure, and yet I would like to be able to apply thermodynamics to it, or I could scale up all the molecules of a gas or water and have them be gigantic on some scale, but for whatever reason I can't see them. Maybe I have to put on some special glasses to see these things. Suddenly they become visible to me. But so it seems to me it's not so that heat is sometimes associated with the microscopic is just the accident that the microscopic is invisible to us in certain contexts. There is an interesting mathematical underpinning here. I just want to flag. I won't go into this in a lot of detail, but one thing that's being said here, you notice I've really dramatically reduced the number of variables I'm talking about. I went from 10 to the 23 configuration variables. They're now all projecting down onto effectively one that would be the entropy variable when psi can be written as TdS. So you are projecting out those unobservable degrees of freedom and trying to design a physical theory without them, and that is thermodynamics. And when you do this projection process, there is a precise mathematical structure that you get, which I call a contact system. It is a contact geometry together with a Legendre submanifold, and which contains the deep structure of thermodynamics. Arnold was referring to contact geometry in that quote from the beginning. This is a just very brief preview that I hope, for those of you who've already seen it, you already know, but I hope for those who haven't, this is a underappreciated structure in mathematical physics. For some reason, we all learn of Cartan's geometries, but not this one. We learn about Riemannian, pseudo-Riemannian geometry. We learn about symplectic geometry, but we don't learn about contact geometry. This is, in a sense, the odd-dimensional analog of symplectic geometry that we use to understand Hamiltonian mechanics. It gets used in contexts like extended phase space in Hamiltonian mechanics. You put a time variable into Hamiltonian mechanics. Now you have an odd-dimensional manifold. There is a canonical way to convert the symplectic form into what's called a contact form when you do that. So extended phase space lives in this sort of geometry. People who do scale invariant cosmology, like shape dynamics people, will effectively mod out by a one-dimensional symmetry. And that takes you from a 2n dimensional structure that is the symplectic system down to a 2n minus 1 dimensional structure. And it appears here in thermodynamics. You have a manifold, you have a special one form, which defines a distribution and in fact the sets of vectors that it sends to zero that gives you a field of hyperplanes at every point on the manifold. So, a manifold with a one form can always be viewed as a field of hyperplanes. This one just has the virtue of being maximally non-integrable. Integrable in the sense of Frobenius means that you have a surface that can thread all of these hyperplanes. And the question is, in what dimension is that possible? Here, this is a sort of maximally non-integrable system. So this is the Frobenius condition without the n. It would be 0. Here it's non-zero all the way up to n, where in figures into this 2n plus 1 dimensional manifolds definition. Anyway, this feature of this physically is that you can always take a gadget like this and use something like Darboux theorem to write it in terms of P's and Q's. But where my P's and Q's are going to be things like canonical pressure and volume instead of canonical momentum and position. And you get all of the nice structure of thermodynamics, the laws, the Maxwell relations. You can talk about phase transitions. It's a lovely thing. And mathematicians sort of look at this. So for me, this is a nice target, and it falls very naturally out of this interpretive perspective, philosophical perspective on what thermodynamics is. So, and the last bit, and I wanted to leave plenty of time for discussion. Yeah, go on. Yes. Great question. Great question. You can't, the answer is you can do, but this structure is more general. Yes, yes. So what I find particularly lovely about this kind of framework is that ideas that don't always have a precise mathematical expression the way we talk about them in the first lectures of thermodynamics can now be made quite precise. And equilibrium is one of those things. We often say these laws apply to equilibrium systems, but we'll be thinking in terms of physical examples when we define that word. But if you want to get really conceptually sharp and express it with mathematical precision, that's often missing from your first textbooks in thermodynamics. Here, there's a number of options. There are a number of different kinds of equilibrium that one can express in this language. So the concept separates a little bit. But one is, for example, that energy is extremely stable and would be expressed as a concave function. And this turns out to be equivalent to entropy being extremized as a convex function. So there's that equilibrium concept is tightly connected to the second law, in effect. The way I look at these systems, though, you know, I wrote it down as m theta L. That's sort of like writing down mg for a space-time, where usually you're going to add on a lot more. You'll have a free bosonic field, you'll have a stress energy tensor, you'll have more things that give it more structure, energy conditions, causality conditions. And here, the thermodynamic system is being treated like that. As you add in more structure, you get to talk about things like equilibrium, the second law, the Maxwell relations, phase transitions, but it's sort of like adding structure to a base thing, which I think of as thermodynamics because it involves heat. Yeah. It's lovely for that, for that kind of analysis. Yeah. I mean, those are often expressed in the first instance as statistical theories. But again, like, part of why I love this treatment is that when Bose and Einstein were first investigating that structure, they didn't know what it was made of. You know, they didn't have a good grip on the, you know, quantum field theory physics underpinning it. And so you can be directed by thermodynamics like as a guide on where you should go. You know, sometimes in foundations we say to ourselves, like, don't take thermodynamics too seriously because, like, that's not the real theory. Underneath it, there's a quantum stat-mech theory. And that's what's really guiding our understanding. But when we're in the position of not knowing what's going on, like in black hole physics, you know, there's a dramatic lack of information. This is our friend. And that's where we were when we were Clausius and Kelvin and Planck. Like, they didn't know what they were looking at, and that's why they developed this theory. So I see this thermodynamics understanding as being something that helps one analyze the past, but it's also sort of dramatically helpful tool. It's a friend we have lived by in recent years for studying physics to the future as well. Yeah.
Sorry. It seems like would you comment whether they're the same or?
Oh yes, they're not the same. I'll show you. So you're getting at a question that it will be helpful to say something I wasn't going to spend a lot of time on about the Legendre submanifold. But I'll give you a brief aside. I mean, the structure is really interesting. So if you're into this, I'd be happy to show you briefly. Oh, you have the good chalk. It's a delight, isn't it? Just a bit. No, it's all I need. I'm about to have an amazing experience now. Thank you for this. So we're dealing with a manifold M of dimension 2n plus 1. Now, I'm describing this at the sort of most general mathematical level at the start, but one can turn things around and look at this the other way, beginning with some other gadgets. So let me say I've got a smooth function u that I want to be energy. And I've got more smooth functions like T and S that are going to be temperature and entropy. And these are how I understand heat, where heat, this was the heat one form, is written in appropriate contexts as TDS. Certainly not always, but in certain situations it is. And then, I've got some further variables, P and V, that I'll interpret as something like pressure and volume. In terms of these familiar variables, like physical variables, theta, so this is, I'm imagining an ideal gas right now. The formalism is more general. It could be any number of sort of work variables that you want. But let me just take this simple. So this is really a 5-dimensional manifold if I just pick these as smooth coordinate functions, 5 smooth coordinate functions. So then theta looks like, let me get the signs right. Minus TDS. Whoops, sorry. I wanted psi there, minus PDV. Where again, I've written psi, but I'm meaning it now to stand in as TDS. Now, this is a 5-dimensional manifold. On that big 5-dimensional manifold, there are lots of paths that in thermodynamics we would call irreversible. They would correspond to irreversible processes in which I wouldn't expect the first law to strictly hold. It is a special situation in which the first law of thermodynamics holds, and it does so on a certain surface, which is just mathematically like a constraint surface, but it is here called a Legendre submanifold. L is a surface on which this one form vanishes. So this is the pullback of the one form. The one form's defined on, I'm just being pedantic about how I write a submanifold. I've got the whole 5-dimensional manifold. This is going to be a 2-dimensional thing, L. So I've got L is dimension 2. And I consider a map that takes L into the manifold. That's in effect going to allow me, when I coordinatize L, I'll choose 2 coordinate functions. I could choose any of these and get the adapted coordinates from it. But whichever 2 I choose, the other ones become functions of it. This gives me equations of state. I'll now have a bunch of functions of, say, P and V. And now I've got a PV graph, and the other, energy is a function and entropy is a function. But I could have chosen other adapted coordinates. So if I choose, ST, then I've got an ST system. The other things become functions. But in general, what I want to look at is a surface on which this thing vanishes. So I look at the pullback of the one form just to be pedantic about it. But when I set this equal to 0, so on L, you have 0 is equal to this whole thing. And that is, in effect, the first law. If I pull the energy over to the other side, or pull these 2 over to the other side, you're just looking at the first law when this is set to 0. So the significance of this Legendre submanifold is you're choosing a surface on which the first law holds. And that's sort of how you do these analyses. If you're looking at a thermodynamic system with the first law, you'll always have this triple, and you can sort of play with all those things. But yeah, it's important to distinguish heat from this one form, which is sometimes called the Gibbs one form or the contact one form. Sorry, very mathematical aside, but I am an evangelical at the moment for this particular framework. I'm finding it really powerful and helpful. It lets you analyze a lot of stuff. Recently, I saw a talk by John Baez on YouTube. This is again for the YouTube channel people. Check right now inside your YouTube search bar for John Baez talking about the Maxwell relations and thermodynamics. He notices that these thermodynamic expressions, which involve partial derivatives of these sorts of variables, S and T and P and V, those equations have the exact same mathematical form as Hamilton's equations. And he just went into this talk being like, why? It's so weird, you know? And he gave this classic John Baez talks where he just like explains in elegant detail where this comes from. But he doesn't really drill down to the deep structures underneath that, the deep mathematical structures. What is really going on is there is a contact structure here, which connects the theory of thermodynamics, it's just sort of in mathematical form, to Hamilton's equations, because a contact structure is associated with a symplectic structure and vice versa. You can go back and forth between them by looking at an extended phase space. Yeah, I can highly recommend looking into this more. It's quite fascinating stuff. But I know you get a lot of people who say, look at this difficult mathematics, you should do it. So, you know, just my own opinion. Finally, on Beckett-Jean entropy. So again, going back to this just so story that Beckett-Jean was just sort of an errant PhD student who got lucky, you know, but the real thermal stuff came from Stephen Hawking later. So going back to how I understand what thermodynamics is, you've got a little chunk of energy, you've got the unobservable part and the observable part. Now let's look at the classic expression of the first law of black hole thermodynamics. Now M is the mass of the black hole, kappa is the surface gravity, A is the area, and omega and J are your angular momentum and angular velocity terms. My claim here is that the same sort of thinking applies where non-measurable will be defined for those observers who are not on their way into the black hole. They're exterior observers. I'll give two examples to illustrate how I think that would be done. I think more can be done here. This is sort of just a start, but I want to point out the rough idea I have in mind here of interpreting the first law of black hole thermodynamics, even as it's formulated by Beckett-Jean, before I even do Hawking radiation and StatMech. There's a sense in which this is describing heat as unobservable energy. So first, Penrose processes. This is this weird thing that you learn at some point late in your GR course where you're like, you're already convinced that you can't take things out of a black hole. And then they're like, well, except you can take energy out of it. And very surprising, but true fact about the Kerr solution, it has this ergosphere in which here's now the exterior observer who drops a particle, positive energy, into the ergosphere. Not yet across the horizon, though. And it splits whilst in the ergosphere into a positive and negative energy particle. So I wrote negative in orange and positive in pink here. And assuming that the local energy of this particle is conserved, that means that the thing, so the pink one goes back to the exterior observer, the orange one falls into the black hole. And we now ask, what kind of thing does the now later time exterior observer receive from this pink particle? And the answer is it's something that has more energy than it started out with. You had some energy associated with this particle. Now you've taken away negative energy from it, sent that into the black hole, it's gone. And so its total positive energy now on the pink line here is less. So weirdly, you have extracted angular momentum. Well, sorry, I'll get to that. You have extracted energy from this black hole in the ergosphere. And through a now well-known analysis, you can find it in classic textbooks like Wald. One can identify exactly what happens as you do that. You are spinning down the black hole and extracting energy from the angular momentum degrees of freedom. But there is a limit to how much you can do that. I would put it this way. The accessible energy is exactly the angular momentum terms in the black hole first law. But you cannot extract more than that. You will still be stuck with, the black hole will continue to have, once it becomes a static black hole, this area term, which is inaccessible to you. So I'm in a position in this interpretation of thermodynamics of having to begin by telling you what I mean by observable and unobservable. In a dynamical system, it was easy. I was like smooth function representing a pressure gauge. Now it's a little more complicated. So I'm giving you sort of a hand-wavy argument, or sometimes people say a physical argument, of a person who is extracting energy, so I know what it means to measure energy. It's like whatever this exterior observer does to measure the energy of this particle. And with respect to that notion of measurement, the accessible energy is indeed what we usually call the work term in the black hole. And the inaccessible or hidden energy or unobservable energy is the area part associated with the horizon. This, however, is a little bit hand-wavy, so I'm now going to tell you a slightly less hand-wavy thing, quite a bit less hand-wavy thing, but I won't go into a lot of detail into this because this is by itself a whole talk. And there's a lot of things I don't know about this next question. So the second way in which you could view the non-observable energy as somehow associated with horizon energy is using Wald's covariant phase space formalism developed in a paper with Bernard Kay in 1991. And in this famous paper of 93, I think, called something like black hole entropy is Nutter entropy, gives rise to the name Wald entropy. It's a cool thing. And basically, I mean, the reason why I thought this would be the way to go is because it is an analysis in terms of dynamical systems of black hole thermodynamics. The easiest case for me is to be looking at a dynamical system and then start applying this kind of thinking, asking what are the literal observables and what are the unobservables. Was there a question?
I don't.
The very end, yeah. So very brief whirlwind because it doesn't, in 15 minutes, it doesn't make sense to go through this in a lot of detail. This is a perspective in which we construct a configuration space of field configurations, where the fields are normal things that you get defined on a relativistic space-time. So I have a bunch of tensor fields representing matter-energy fields or geometric structures or whatever I want, but I've got a big list and I can consider those fields or their derivatives or their higher derivatives. And I therefore define a configuration space and its corresponding momentum space, cotangent bundle, or I can look at a bigger jet bundle and go up and up and up with all the derivatives. So it's really quite general configuration space structure associated with fields defined on a relativistic space-time. And so I'm going to choose the classic one of a collapsing star that Hawking writes down for the formation of a black hole in which he analyzes Hawking radiation. But we're not going to do the Hawking radiation calculation here. We're instead going to isolate certain kinds of fields and distinguish them from others and use them to give a derivation of something that looks just like the first law of black hole thermodynamics, but which Wald gives a slightly different interpretation. I look at what's happening in the following way. If you're outside a black hole, we'll use this again, sort of physics approximate way to talk about the universe, where we'll say infinity means a long ways away. Not really infinitely far away, but just pretty far away. So if I'm trying to imagine where I, the observer, am with respect to one of the two black holes that you've now photographed here at the BHI, I'm at the literal spatial infinity point. So I'm going to go all the way out to spatial infinity. And then there's a certain class of fields that I can measure and I'm interested in from that perspective. They are the ones which have support. That is, they are, pretty close to well, they're basically non-zero. I say basically with some mathematical caveats, but they're basically non-zero exactly outside the horizon. Those things that are, those fields that are non-zero outside the horizon are those ones I have good control over. I can measure them in their entirety. They are the ones that are accessible to me from an observable perspective. And one can indeed write this down as an actual observable in the sense of a smooth function on a phase space. And the stuff on the horizon, or indeed inside the horizon, is not accessible. And what Wald shows, the central result of the paper, is that there is a split into exactly two types of energy associated with this sort of field configuration, where now energy is defined using the Einstein-Hilbert action to describe ordinary relativistic space-time evolving in time. We're now using that notion of time translation to characterize Nutter currents. He finds that there are Nutter charges specifically for these fields available to the external observer. And then there are other Nutter charges, which are exactly the ones associated with horizon symmetries. So I've linked here for those ones following the slides, some papers on this topic, but here's like a picture of how this looks in practice. Over here, you have the BHI telescope people observing what is really a field configuration, which has support in the exterior region of a Hawking-style black hole.
Why don't you want to?
Yes, you can do that too. You can do that too. Yeah. Yes, I mean, I just chose this kind of Cauchy surface, but as long as you have a Cauchy surface, then you're fine. Basically, I've drawn it as a Cauchy surface, but yes, you could choose a null one as well.
Wouldn't be Cauchy.
Well, it depends on your definition of Cauchy. I mean, it could be forced to be space-like, but you can have a null surface that is Cauchy. I mean, Minkowski space-time, for example. Going the other way, you mean? Well, I mean, yeah, like this one, for example, yeah, it's not a Cauchy surface. Okay, yeah, sorry, maybe I'm misunderstanding, but there's, anyway, this is, the thought simply is, we'll define some field configurations which are explicitly accessible to us here at the BHI. And then there's some field configurations which are not, which indeed would also include stuff that's in here. But it turns out that this symmetry along the horizon turns out to be all that you need to get the entirety of it. So this is, Wald's theorem can be expressed in this kind of way. The energy associated with this field dynamical system is the stuff associated with the horizon entropy, which in certain special cases is kappa dA, where stationarity holds. But this is in a sense a generalization of the original black hole first law. So this gives you one of the terms, this gives you the other term, and they're just exactly the accessible and inaccessible components of energy of the black hole by my lights. So this is again the lesson: when horizon degrees of freedom are hidden from measurement, they contribute to heat, and so the black hole is thermal. Before I even mention Hawking's analysis, again, this is not to say we don't need Hawking's analysis. This is obviously a crucial part of understanding black hole thermodynamics. But I just, as a person who understands thermodynamics to not just be a thing of the past, but also of the future, I think it's important that we not call Bekenstein an errant PhD student. It was a good analysis. It was really thermal. And indeed, here's what he says. We take the area of a black hole as a measure of entropy, entropy in the sense of inaccessibility of information about its internal configuration. And people complained about this, like, oh, information isn't physical. Okay, you have to be a Wheeler extremist about getting it from bit. But replace information with degrees of freedom or energy associated with those degrees of freedom. And it has nothing to do with information theory per se, and everything to do with the dynamical system and its observables. So this, again, is the better story I've been arguing for. Thermodynamics is the science of heat as unobservable energy. If you adopt that view, even without StatMech, black holes really are thermal. Thank you.
Thank you. Have lots of time for questions.
So I have two quick questions. One is a follow-up to Mesh's question. Equilibrium case. Let me quickly start with that one. So in my very naive understanding of the intertheoretic reduction of usual way we present thermodynamics, statistical mechanics, I think about a statistical mechanical approach to some, I'm usually considering a classical system. I think in terms of microstates and macrostates. And I think about equilibrium as being the statement that I have well-defined macro variables like pressure and volume and so forth. When I'm out of equilibrium, I generally don't ascribe those macro variables to my system. So I'm a little concerned about the generality of this thermodynamics first approach when it comes to non-equilibrium systems when I don't. So I recognize, of course, that I don't know what my system is made out of. All I have access to is a bunch of macro variables. Granted, I'll need to use a system like this, but I think in that case, I'm limited to the equilibrium case, right? I need some finer grained microstructural understanding of my system in order to be able to talk about non-equilibrium dynamics when
Good,
these
good.
variables might not be available.
Good.
So I've always
I get the
been
question.
confused about this. If you could clarify.
Yeah, great. So question, I also had this question at the start. You know, it really feels like equilibrium is essential to how I understand the meaning of these thermodynamic variables when I think about how they're defined physically. How can I possibly have such a general structure? It seems like it would just break down and not be useful in those contexts. Let me try and paint for you the picture in which it is not just useful, but helps one go beyond some of the historical puzzles about thermodynamics. I feel a lot of the reason we've struggled to interpret thermodynamics, and indeed the reduction problem, is because we've had this sort of overemphasis on equilibrium in the development of thermodynamics. The basic thought is, when you build a stat-mech system, I'll just think about classical stat-mech, but analogous things can be said in quantum stat-mech. In classical stat-mech, there's sort of two steps to building the statistical analysis of mechanical systems. First, I have a set of observables. They define a coarse graining. And then I have, second, a probability distribution associated with that coarse graining, which is weighting them differently. And it could just be the so-called Liouville measure. That would be what you naturally get the natural volume form out of the structure, but it could be weighted differently depending on what's going on. The significance of the observable step, I think, is underappreciated. What you're doing there is saying something that has a lot of interesting physical content at the outset. When you say, I have a set of observables, and I'm now using them to coarse grain the system, what I'm saying is, these observables won't make all the distinctions because it's not all the smooth functions. I mean, that's kind of a crucial postulate. It's not all the possible observables. It's a reduced, smaller set of them. So there will be states in this manifold which are not distinguished by the observables in the sense that they get assigned the exact same values by all my observables. So that's like I checked with my pressure gauge, I checked with my rulers, and I keep getting the same result. So I will say they live in the same macro state. And that just doesn't require statistics to express. It doesn't require time translation and variance to express as one thing associated with Gibbs equilibrium. It doesn't require being the largest or the smallest as associated with Boltzmann equilibrium of these macro states with respect to some measure. It just involves what I can and cannot see. This is extraordinarily helpful. So I begin with just that mechanical system. I take the coarse graining step, very similar to how you would do it in stat-mech. But now I haven't brought in the statistics at all yet. I could do at any stage, but I haven't done it yet. And I have built just out of this structure what thermodynamics means. Now, here's a problem with thermodynamics that this helps us solve. People often say about thermodynamics, look, it looks time irreversible, whereas mechanics is time reversible, at least without weak interactions. Or thermodynamics has no fluctuations. It only has the monotonic approach, to equilibrium, as it were, whereas statistical mechanics fluctuates out of equilibrium. How can I deal with that sort of thing? I think that we've been imprecise about thermodynamics in both of those two statements. We haven't said what we mean by thermodynamics. And I can now just as well put on a probability measure on my thermodynamic system as I've just defined it. And that gives me a mathematical structure, which already has been studied happily by mathematicians, which is the study of statistical thermodynamics. It's looking at statistical mechanical variables and introducing fluctuations in a way that you might have thought looked ad hoc. It's like I just threw this in to make a broken theory work. But by my lights, it is just doing what we do in stat-mech and can be motivated in similar ways. You introduce a notion. So if your notion of equilibrium is statistical in nature, then you can define it now in thermodynamics using that probability measure. And similarly for other notions of equilibrium. So I find it actually helps. And I hope I sort of explain why you don't really need statistics to make this move. Sure.
The question is much more complete. Sort of, how do you define temperature not quasi-stationary?
Yeah,
It's
yeah.
fine, I think
Oh, sure. Yeah. Okay, so
The black hole.
yeah.
Thank you.
Sure. I mean, that quasi-stationary argument, on that quasi-stationary argument, so this is the argument invented by Clausius, which says like, okay, imagine I'm moving along a curve pretty slow, and I'll imagine I can always move backwards along another curve, which is reversible, and get back to the same point. And then I'll assume the Clausius law about these curves. And then I'll argue that entropy increases. So I have
So entropy.
define entropy and temperature, right? It's like how Clausius gets temperature and entropy is using this quasi-static argument. I think there's a variety of different ways to analyze heat. For me, this is the mathematical question we're studying here is, I may just erase this nice contact geometry, if it's right. You have an arbitrary one form, and you want to know under what circumstances there exist smooth functions t and s, such that one form can be written like t ds. This is the question of whether the one form has the so-called integrating factor that would be big T, and extensively studied question with lots of interesting kinds of answers. One is the Clausius way. I find this argument a little dodgy, though, and can highly recommend Yasu Fink's paper called Bluff Your Way Through the Second Law of Thermodynamics. So I kind of went in already not loving the Clausius argument. But other ways one can do it involve Curie-Theodori's theorem, another mathematician's way, but it starts with a certain assumption about what's accessible and not accessible in thermodynamic phase space. And yet another way that I worked on and appears in this archive paper, it's really a tradition due to Jauch, Joseph Jauch of like quantum electrodynamics fame, and also the Jauch-Piron theorem and the foundations of quantum mechanics. Also, at the very end of his career, before he sadly died of lung cancer, he wrote 2 papers on thermodynamics in which he was mostly focused on this question and pointed out that there's a certain conservation law which you can associate with the existence of these kinds of smooth functions. And that conservation law is roughly the conservation of accessible work. So if the black hole exterior observers have a certain kind of, they have a concept of work now, the energy that is accessible to them, if it is conserved in a very classic sense, meaning in the configurations, field configuration space going around a loop, the total work around that loop is 0, then an integrating factor of this kind exists. So there's sort of, for me, this is an important mathematical question. It's not always available, being able to write it like this, but that's actually okay. In the Wald paper, where he's doing a much more general treatment of black hole thermodynamics, he points out that you can't always write down kappa dA as the heat of a black hole. His approach is much more general, right? If we're looking at a more general black hole spacetime that might not be stationary, then this term is not just kappa dA, but it gets more complicated. So I think this is actually a virtue that, firstly, that it's not always so simple and immediate that you get to write down TDS. But second, the mathematicians have spent some time developing the tools to know when you can do it. So yeah, sorry, this is roughly what I would say. Happy to chat more, though, about this topic.
Okay. I had a question, but I was worried about that. But very quickly, I was just worried. My question was about observability. So obviously, I mean, just naively, temperature is observable, and it's true that we don't like have entropy. The black hole case, back out the area.
Yeah, great question, great question. I had thought about the temperature thing a little bit. I think one needs to distinguish, here it matters exactly how I put this claim. I am interested in whether these little quantities of energy are accessible to me. And accessible can mean a lot of different things. I'm using observable. in practice, for the Penrose observer, the Penrose process observer, I'm literally extracting work out of the black hole that I can use to sort of spin a flywheel or do something interesting. And the term kappa dA can't be used in that way. Even if I have some argument that the A should be this or that, that the area is what it is on the basis of my observations of the geometry, the energy is inaccessible to me. It is associated, it is unobservable in a certain precise sense, as an observable on the phase space. So, I mean, it's why I think to make this really clear, one does have to get sharper and look at things like the covariant phase space formalism, where I'm asking now a question about whether there's an observable, on this field algebra, which is something corresponding to a measurement device. And the claim would be that there isn't for that, despite the fact that, I can take a temperature, a thermometer and stick it in a gas. Yeah.
All right, there's
economic. Is